The story of OceanGate's Titan submersible is a tragic one that revolves around a small diving vessel designed for exploring the depths of the Titanic wreckage, situated 3,800 meters below the surface of the sea. In order to understand how this submersible and its various systems operated, it is essential to delve into its intriguing features, ranging from propulsion mechanisms to communication systems, some of which functioned as intended, while others tragically did not. Additionally, one particular system was even designed to dissolve underwater. Let's embark on a brief overview of the Titan submersible. The primary objective of the Titan submersible was to descend as deep as 4,000 meters underwater, an environment characterized by extreme pressure, darkness, cold temperatures, and limited communication capabilities with the surface. These challenging conditions exemplify the difficulties associated with deep-sea exploration. The entire Titan system weighed approximately 10 tons and consisted primarily of several core components. The most significant of these was the carbon fiber hull, which ultimately became the vessel's weakest point and tragically led to the loss of all those aboard. The hull, 5 inches thick, succumbed to the immense pressure during the 7th dive to the Titanic, imploding much like a railroad tank does when subjected to a vacuum. This implosion occurs due to the pressure outside the structure being significantly greater than the pressure inside. In the case of the Titan, the implosion would likely have transpired even more rapidly. This raises the question of measures taken to prevent such catastrophic failures. One approach involves creating a virtual model of the submersible to test its limits. However, modeling carbon fiber is notoriously challenging due to its intricate composition, comprising numerous thin fibers interwoven and cured together. This complexity introduces various possibilities for weakness as layers shift and separate. Unfortunately, without destructive testing to fully explore the limits of the Titan, these models alone were insufficient. To address this limitation, the Titan submersible incorporated a real-time acoustic monitoring system. According to a patent held by OceanGate's CEO, Richard Stockton Rush, this system utilized multiple small sensors, including ultrasonic microphones and strain gauges, to monitor vibrations in the carbon fiber hull. Regular data collection and transmission to a centralized system enabled analysis of the hull's internal and external structure, facilitating the prediction of potential failure conditions. However, this type of testing was relatively new, and in hindsight, it proved inadequate. Concerns were expressed by the Marine Technology Society, stating that the design of the Titan had the potential for catastrophic negative outcomes. The use of carbon fiber and the tubular shape were both concerning aspects, with the latter being less effective at distributing the pressure exerted by the weight of the ocean compared to a spherical shape. The Titan's end caps were composed of titanium and affixed to the main hull using 18 bolts, thereby preventing passengers from exiting through them. The viewing window, reportedly certified for depths of only 1,300 meters, merely 1/3 of the Titanic's depth, also posed a significant concern. These components were tested together in collaboration with the University of Washington using a 1/3 scale model. During this testing phase, a former employee named David Lockridge expressed concerns about flaws in the carbon fiber under pressure. Beyond these critical design considerations, it is essential to understand the operational mechanisms of the Titan submersible and how it navigated its surroundings. After receiving an initial briefing, The first step in a Titan launch involved deploying the docking station from the main ship. This classification as a submersible rather than a submarine is due to the inability to depart and return to port autonomously. The docking station would fill its ballast tanks with seawater, increasing its weight and causing it to submerge 9 meters underwater. At this point, the Titan would detach and commence its descent while the docking station refilled its tanks with air, causing it to float back to the surface. This process would be reversed at the conclusion of the voyage. To facilitate movement, the Titan submersible was carefully balanced to maintain neutral buoyancy unless the electric thrusters were activated. With a total of 4 electric thrusters provided by inner space, the submersible could maneuver in various directions, including up, down, forward, backward, and rotationally. These thrusters were designed to operate highly efficiently in both forward and reverse directions. Power for the motors was supplied by an onboard battery system similar to those used in electric cars. While media scrutiny has focused on the use of a game controller for submersible control, this approach is actually quite common in military applications due to the controller's ease of use, durability, and accessibility. Game controllers are currently employed worldwide to control a wide range of devices, from explosive disposal robots to Virginia-class attack submarines. In addition to the game controller, the Titan featured touchscreen displays that provided visual feeds from external cameras and text messages transmitted from the main ship on the surface. Deep-sea exploration requires substantial lighting for cameras to capture anything in the dark ocean depths. To meet this need, the Titan submersible boasted external lighting with a luminosity of 40,000 lumens, approximately 40 times brighter than a car's headlight. Communication between the Titan and the surface ship was facilitated by an ultra-short baseline acoustic system. Acoustic pulses were employed in a manner similar to Morse code to convey messages. This system had previously been utilized to direct the Titan to the Titanic wreckage during past voyages, as the submersible lacked its own navigation system. To determine the Titan's location, the surface ship employed an acoustic positioning system. The ship emitted an audio frequency from a transducer, and when the Titan's transponder received it, the submersible responded with a corresponding signal. By measuring the time taken to receive the response, the surface ship could calculate the distance to the Titan. By using multiple transducers, the ship could also determine the direction from which the audio wave originated. Combining these measurements allowed for precise localization of the submersible and enabled the transmission of directed messages to guide it toward the Titanic wreckage. Given the tragic outcome of the final voyage of the Titan, one might question the effectiveness of the safety systems on board. It is crucial to recognize that in all emergency scenarios where passengers remain alive, such as power cuts or communication losses, resurfacing would be the optimal course of action. However, in the event of a fire, additional measures were required. As a result, fire extinguishers and smoke masks were available for all passengers. Resurfacing would still be prioritized, but these additional safety measures were in place. To facilitate resurfacing, the Titan submersible possessed 7 systems designed to help it ascend. These included powering the electric thrusters, inflating an air balloon, and dropping lead weights. Notably, one of these systems incorporated a dead man's switch made of a material that dissolved upon exposure to salt water. After approximately 10 hours of diving, This material would dissolve completely, releasing sandbags from the submersible's bottom. This weight loss would provide the submersible with buoyancy, initiating its ascent toward the surface. These safety systems would only be effective, however, if the hull remained intact. The loss of the Titan submersible was a devastating event, leading to the loss of valuable human lives and raising significant questions about deep-sea exploration technology. The investigation into the incident remains ongoing, with the hope of learning valuable lessons and implementing necessary improvements to prevent such tragedies in the future.